We now move on to a slightly different problem which also rests on this definite integration, to evaluate definite integrals, and as I've written down, we are going to focus in this lecture, this part of the lecture, on volumes of solids of revolution. We have to give a meaning to this solids of revolution. We have taken as a very simple illustration a rectangular area that has this point can be taken as h0. That means its length is h and its width is taken as r. So we wish to find something called a volume of revolution or volume of a solid of revolution. Now it's very easy to understand that from this area we can create a cylinder whose length is h units and whose base radius is r units. How? By taking this and giving it a full rotation of 2 pi radians about the x-axis, If we do that, then we will get, I think I'll draw the other part like this. If we make this area rotate about the x-axis, then we generate a cylinder which is a solid of revolution. Of course, there is no part going this side, so this is the last part of the cylinder. Just for understanding, I am doing this. That is understandable. If I take, for example, another case, we just take, for example, a parabola like this. This is a area. If we rotate this about the x-axis by 360 degrees, then we get something that resembles a cup. So that's called a paraboloid. The plane curve is a parabola. Now we get a paraboloid. Parabola to paraboloid, ellipse to ellipsoid, and so on. Of course, if a circular or semicircular area is rotated, we get a sphere. But the important part is to first appreciate that when areas are rotated about specified axes, they will generate solids of revolution, and then the task is to find a volume element and to integrate between limits to generate the total volume of the solid being formed by rotation of specified areas. Now we start with the very simple example, the first rectangle example. Let's see what we get as the solid of revolution. Before that, we have the very pleasant task of defining a volume element for integration. If we take any strip of this area here like this and rotate it, one can imagine with very little difficulty that one generates a coin, which is a cylinder but with a very small thickness. So that coin would have a depth given by dx and of course it will have a certain amount of area. Now, if we look at the volume of this coin, being a cylinder, it's pi r square h. So, here we can write the volume element is pi. The r is taken as r, we can take it as a. We had written r here, so this we keep as the radius. So pi r square dx, because this is the width of the strip. The width of the strip is here is dx. So in this particular case it is pi r square dx, but if we had a varying, if we had a curve, for example here, if we come here, we see that a strip would be pi y square dx. The coin would have an area of a volume of pi y square dx. There is nothing different between pi y square dx and pi a square, because here the equation of this curve is y is equal to r. So that's why pi y square dx holds as much for the cylinder as it does for any general curve. So if we integrate for this particular case, the volume of the cylinder is integral 0 to h of pi r square dx. This is nothing but pi r square is out into h. This formula for the volume of a cylinder is very well known to us. Now we will use this volume element, that means pi y square dx, as dV to find the volume of a hemisphere or a sphere. Actually we are looking for the volume of a sphere. Again we take simple examples, because all of us know that when we take a sphere, its volume is 4/3 pi radius cubed. I repeat, the volume of a cylinder is known to be 4/3 pi r cubed. So we take a simple figure so that the result that we get, we can marry it with known results. One moment. Excuse me. We rub out all that is there on the board and maintain the following, that volume is an integral of a volume element is equal to integral pi y square dx, assuming that the function being considered is y is equal to fx. Now we draw that quadrant of a circle once more. This is the full circle. We draw a quadrant of a circle, or rather the full circle. We take a small strip like this, strip of area, and imagine that if we rotate this entire area, this part of this quadrant about the x-axis, through 360 degrees, then we will get the volume of a hemisphere, and the volume of a sphere is double of that. So what we do is, our required volume is VR required is 2 times the volume of a hemisphere. So 2 times pi y square dx. If we reckon that this is a, the radius of the hemisphere of the sphere is a, then we have to integrate between limits x is equal to 0 to x is equal to a. This point is a0. So we put the limits 0 to a. So if we can integrate this, we get the volume of the hemisphere, because we've started the integration from x is equal to 0 to x is equal to a. We multiply that by 2, we should get the entire area. Now we can rub out this diagram, or maybe rubbing out this part will help. The entire diagram need not be rubbed out, because the integration is indeed very simple. When we say y squared dx, the circle, the bounding curve has an equation x square plus y square is equal to a square. So in other words, this implies that, my friend, y square is a square minus x square. So we substitute that here and write this is equal to 2 pi integral 0 to a square minus x square dx. This is going down, so we just evaluate this in 2 lines up, take it up and carry on the calculations. So this is 2 pi times a square x minus x cubed by 3, 0 to a. This is 2 pi times a cubed minus a cubed by 3, that is 2 times 2 by 3 a cubed, and this straight takes us to 4 by 3 pi a cubed. This is what I was talking about. This is cube, not square. That yes, indeed, we've again proved that we can go home and carry with us the result that the volume of a sphere is 4 by 3 pi a cube. 4 by 3 times pi times the cube of the radius. Did we learn that earlier? Yes, in school, high school, we were told, when we were given formulas about spheres and cones and all these things, we were told that the volume of a sphere is 4 over 3 pi r cube, and its surface area is 4 pi r square. We will tackle that in a separate lecture, the surface area part, but I wish to evaluate in this lecture a little more. I wish to evaluate the volume of a cone, C-O-N-E,